Hello everyone. So today we'll be discussing about vectors. Okay, we'll start introduction of the vectors and then later on we'll go into the other parts. Okay. So first we'll start discussing about the difference between vectors and scalars. Right. So when we talk about scalar quantities, what are they? These are those quantities. Look at this. Scalar quantities are those quantities that have only magnitude and no direction. Can you give me some examples of scalars? Examples of scalars, everyone? When you think of a few examples which do not have any direction at all. Yeah, mass, one classic example. Time, another example, does not have any direction, right? Mass and time do not have any direction. Then you can say volume, you can say density, right? And remember, area is not a vector. Area is not a scalar. Area is a vector. For area, we can define a vector. We'll learn that later. Volume is a scalar, density is a scalar, but not area. Okay, then again, obviously we have others as well. We have distance, we have speed, right? Distance and speed are also some examples of scalars. There are many more examples, but I'm only giving you few. Simple. Okay. Now we'll talk about vector quantities. What exactly are vector quantities? So vector quantities are those quantities. Look at this. First of all, they should have both magnitude and direction. That is fine. They have both magnitude and direction. But in addition to that, there is one more condition, which is very crucial. That is, they obey the vector laws of addition. So when we say vector laws of addition, there will be two laws. One will be the triangle law or the parallelogram law. Now, if triangle law is followed, automatically parallelogram law will also be followed. So need not worry about that case. It has to follow any one of the vector laws. Okay, that's a very important condition to decide whether a quantity is a vector quantity or not. So let's talk about a few examples of vectors here. Examples of vectors. Can you think of any? Think of a few examples of vectors. I think the best one would be force, right? Force has direction. You can apply force towards right, towards left, up, down, anyhow, right? So force is an example. Then obviously we'll start with terms regarding motion. Position is an example of a vector. Displacement is an example of a vector. Then you have velocity, which is again an example of vector. We have acceleration, which is an example of vector. Right, we'll be going into many other examples as well as you proceed further. The classic examples, right? Simple. I told you there is another vector called as area vector for area. I'm just mentioning it here so that you do not get confused. Going further, you learn about what area vector is. Simple, no? Okay. Now I will mention the importance of the second one. Look at that. Any quantity, to be a vector, it has to obey the vector laws of addition. I'll give you a simple example. We'll discuss about that as well. Now, and the example is current. Think of current. Think of current. Do you think current is a vector quantity? In class 10th, you would have learned about this, resistance and all. So, if you have a resistance in any circuit, so current can either go towards right or current can either go towards left. So, current has direction. Current has direction towards right or towards left. Current has direction. Obviously, current also has magnitude. But current is not a vector. Even though it has magnitude and direction, current is not a vector. Now, why is that? It is not a vector because it does not obey vector laws of addition. Current is not a vector. Not a vector, even though it has direction. Even though it has direction. The reason is what? Because it does not obey vector laws of addition. It does not obey vector laws of addition. Simple as simple as that. I'll give you a simple reasoning behind this. You would not, we haven't yet learned about the vector laws of addition yet, but I'll just give you a basic idea. Let's say I have two forces. Okay, I'll take a simple case, 5 Newton force right and 5 Newton upwards. Okay. Then when you add these two vectors, you'll get a vector whose magnitude will be 5 root 2 newtons and which will make an angle of 45 degrees with the horizontal. Okay. This is how vector addition is going to be. I'm giving you a simple example. How and why you learn that later. Okay. So if you add these two vectors, there is only one possible answer. You have to have a vector, the magnitude as 5 root 2 Newton and the angle as 45 degrees. But will that happen in the case of current? No, because look at this. If I have a wire which is carrying a current of 5 amperes, another wire also carrying a current of 5 amperes, like 5 newtons and 5 newtons. So if they behave as vectors, then the direction of current should be like this, 5 amperes and 5 root 2 amperes and making an angle of 45 degrees now. But will it be that way? No, it won't be that way. Well, it's simple vector addition. If it's simple addition here. 5 ampere of current is coming. 5 ampere of again another 5 ampere of current is coming towards the junction. Then what is going to happen at the junction? 5 ampere and 5 ampere. You add them, and depending on how the wire is, again keep the wire like this. Then both the 5 amperes are added, and it becomes 10 amperes in this direction. When you add these two, you are not getting 5 root 2 ampere. No, you are getting the magnitude as 10 ampere, and direction depends on how the wire is. That obviously means that the current does not follow or obey vector laws of addition, and hence it is not a vector quantity. Clear? Simple enough? Yes? Okay, good. So do not forget the condition that it has to obey the vector laws of addition. Good. And then we'll go into symbols of vectors whenever you write or whenever you show a symbol for vector. For example, for force, generally the symbol that we use is F. But to be clear that it is a vector, we place an arrow above it and we call it as F bar. We pronounce it as F bar. Okay, so any vector or the symbol of any vector should have an arrow above it, A bar. So if A is a vector, it has to be written as A bar, like that. Simple, no? Simple, no? That's what. And one more thing is that the symbol for magnitude of vector. Symbol for magnitude of vector. This also is important. Now, when you talk about magnitude of vector, it is nothing but the value. How much is the particular quantity? Right. So, if I say magnitude of force, it will be this mod of F bar. You know the symbols, right? Mod, mathematically pronounced as mod. Okay. Mathematically, if I say mod of -2, you'll get the value as 2. So, mathematically, mod of a scalar will always give us a positive number. It will always give us a positive number. But here, when we say mod of F bar, we denote magnitude of the vector F bar. Similarly, if I say mod of A bar, I denote what? Magnitude of the vector A bar. Simple. So mod is a symbol used to denote magnitude of vector. Clear? Simple enough? Symbols of vector. So that's it. We'll again continue in the next class.